Hello, my dear students. Welcome back to Shlokas Academy YouTube channel. In the last session, we have discussed about particle nature of the electromagnetic radiations. And in this session, we are going to discuss one important property of electromagnetic radiations, that is, which support the particle nature of the electromagnetic radiation. That is nothing but photoelectric effect, and this is also a part of atomic structure. And in this atomic structure, we are going to discuss about photoelectric effect part 1. And in this part, what we are discussing, we are going to discuss about what is photoelectric effect, how does a metal can eject the photoelectrons, what is threshold frequency, work function, threshold wavelength, kinetic energy of the photoelectrons. All these things we are going to discuss. The first one, what is photoelectric effect? For an example, it is very common phenomena that we can see in our daily life. So here I am taking one metal, right? What is this? A metal surface and one metal strip I have taken. So being a metal, it is composed of metal atoms. What are they? It is composed of metal atoms. For an example, if I take cesium metal, so this metal strip is composed of all cesium atoms in it. Now we know one word, that is ionization energy. What is meant by ionization energy? The minimum energy required to remove an electron from the outermost shell of an atom is called as ionization energy. So in the similar way, so for this cesium metal, under normal condition, it do not eject any electron from its surface. But when a beam of light rays, means a group of light rays are allowed to touch the surface of the cesium metal, means here we are giving energy in the form of what? Light energy. When this light rays strikes the surface of this cesium metal, obviously it ejects the electrons out, right? Means the ejection of an electron from the metal surface when it is irradiated by a light of suitable frequency or suitable wavelength is known as photoelectric effect. And whatever the electrons that are coming out during this photoelectrical phenomena are called as photoelectrons, and the whole phenomenon is known as photoelectric effect. And what is the reason for this cesium metal to emit the electrons? So as I told that here we are giving a light energy which is more than sufficient to remove the electron from its outermost shell. So that means we are giving this required energy to remove an electron from its outermost shell in the form of light, so that the electrons automatically will come out and they will move out of the surface of the cesium metal. And these electrons are called as photoelectrons, and the whole phenomenon is called as photoelectric effect. So that was first given by the scientist H. Hedge, and he had defined the photoelectric effect like this, and by seeing this definition you can make the notes also. Photoelectric effect, right? So how can you define? The scientist Henry Hedge, he had performed a very interesting experiment in which electrons were emitted when a certain metals such as potassium, cesium, rubidium, etc., were exposed to light, and this phenomenon is called as photoelectric effect. Just now I have explained to you by taking cesium as an example, but in this it may be cesium, or it may be potassium, or it may be rubidium. What was the definition? How can you define the photoelectric effect? Tell me. Henry Hedge, the scientist who had done that experiment, right? And in that experiment, what he had observed, right? So the electrons are emitting from the certain metal surfaces, such as potassium, cesium, rubidium when they were exposed to the light, and this phenomenon is called as photoelectric effect. Right. So now what are photoelectrons and how we can explain the experimental setup of this photoelectric effect one by one we will discuss. Right. Here let me take one, what is that, a cylindrical glass tube which is having two ends. So in these two ends, one end we have to insert anode and other end we have to insert cathode. Let me explain first. So here at this end I am inserting one metal electrode which is having positive charge. The electrode which is connected to the positive terminal of the battery is called as anode, and it is also called as collector plate. Why it is collector plate I will explain. And here another metal electrode which is connected to the negative terminal of the battery and which is called as cathode. Right, which is called as cathode. And this positive terminal is connected to the positive terminal of the battery and negative terminal is connected to the negative terminal of the battery. Then when you on this battery, what would happen? Generally, if I on this battery, here there is no connection between positive and negative electrode. That means it is not a complete closed circuit. It must be an open circuit, right? But what would happen? So this metal, this is what metal strip. So to this metal strip, what I am doing, I am supplying a sufficient energy of light rays. What are these light rays? It may be sunlight or any other source of light. When these light rays are striking this metal surface, what they happen according to photoelectrical phenomena? So this metal will eject the electron. What is the charge on the electron? Negative. Being a negatively charged particle, it will attracted by the positive charge. Hence, it will move towards the positive. Initially, there was no flow of electrons between these two electrodes. But when you send a light of suitable frequency on this metal surface, then obviously it ejects the electrons, which causes a photoelectric current in the circuit. So the current which has observed or which has generated due to flow of these electrons is called as photoelectric current. And the electrons which are coming out from the metal surface are known as photoelectrons. And the whole setup is called as photoelectric cell or photovoltaic cell. Right. So let me explain the complete setup of this diagram. Right. So this is what I'm inserting a positive electrode called anode. This is what anode or collector. Why it is called as collector means as it is collecting electrons that are ejected from the cathode. That is why this is also called as a collector, as it is collecting electrons. Right. Next, I'm taking, and it is connected to the positive terminal of the battery, and this is a galvanometer which indicates the flow of current in the circuit. Right. So it is connected to the positive terminal of the battery, and here we should insert one more electrode, that is negatively charged electrode, which we called it as a cathode. This is a metal surface and it can act as a cathode. Right. Now this metal surface is irradiated with a suitable light. Let me take, right, emitter or cathode. This is battery and here vacuum chamber. Right. So this is a light striking the metal surface. Here I am taking, this is a light. It may be sunlight or any other source of the light, and it is going to strike the metal surface. When it strikes the metal, what would happen? Obviously, this metal will eject the electrons. It will give electrons which are coming out from here, and as these electrons are negatively charged, obviously these would be attracted by this positive electrode. So there will be a completion of circuit in this photo due to this photoelectric effect. You can see here the electron is generating, emitting As electrons are emitted by this cathode, it is called as emitter. As electrons are collected by this anode, this is also called as a collector, right? So this total phenomenon, this is what photoelectron, right? Photoelectron or ejected electron. This whole phenomenon is called as photoelectric effect. This whole phenomenon is called as photoelectric effect. Do you all understand? Right, neatly you also draw the diagram in your notebook. Then we will move on to the next slide. Right. And what are the observations that were made during the photoelectrical phenomena? Right. First, let me explain. Then later on, you can make the notes. First, let me explain. So here I am taking a metal surface. This is metal surface I am taking. Any metal you take, it may be potassium or cesium or rubidium, any metal, right? Being a metal surface, when it is irradiated, for example, irradiated with a source of light, the frequency of this light is a mu, right? Mu incident, I means incident light, right? And the wavelength associated with this light is lambda I, which is incident light wavelength, right? And energy of the incident light, EI, energy of the incident light. Now, when a light rays of suitable energy or suitable wavelength, right, or what is that, irradiating towards this, what is that, cathode or metal surface, then what would happen? Tell me. So, being a metal, by absorbing means here we are providing energy to the metal. So then by absorbing that energy, the metal can eject the electrons from its surface or not. And these ejected electrons are called as photoelectrons and the phenomenon. Now what are the observations? Means the first observation, there is no time lag between, means as soon as these radiations, these radiations strikes the metal surface, immediately the electron will come out. There is no time gap. As soon as the light rays touch the surface of the metal, the electron will come out immediately. There is no time lapse. That is very important observation. You should remember. Right, that was the first observation. The electrons are ejected from the clean metal surface as soon as the beam of light strike the metal surface. That means there is no time lag between striking of light and the ejection of electrons from the metal surface. Understood? From the metal surface. So this is the first observation we can do during the photoelectrical phenomenon. Second observation, the number of photoelectrons ejected is directly proportional to intensity. Intensity is nothing but the number of photons per unit area or brightness of the light, right? So if I denote this intensity with I, number of photoelectrons, n is the number of photoelectrons that are coming out from the metal surface, is directly proportional to intensity or brightness of that light. Okay, and what will be the third observation? For each metal there is a characteristic minimum frequency mu naught, right, called threshold frequency to cause photoelectric effect. What is this threshold frequency and what is this photoelectric effect threshold frequency? Let me explain. For example, let me take three examples of the metals: potassium, right, cesium. Only I am taking two. For an example, the potassium is the metal who is emitting electrons by taking some 50 kilojoules energy. Means when it takes 50 kilojoules energy or some x hedge or per centimeter frequency, x hedge per second, not centimeter, per second frequency. So or mu naught frequency. The light rays having mu naught frequency, when it is touching the metal surface of the K, it can emit the, what is that, electron. That mu value is some 150 frequency I am taking, right? So at the same time cesium will also have some mu naught value, but this is not equal to the 150. It may be lesser or greater. That is depending upon the nature of metal. Means the third point, what it is telling means for each metal there is an individual threshold frequency. What is threshold frequency? The minimum frequency required for a metal to cause a photoelectric effect or to eject the electron from its surface is called as threshold and frequency. So that is denoted with a nu naught. Understood? So this is the third observation. And fourth observation, listen carefully. For example, I am taking one metal surface. This is metal surface and it's a threshold frequency. I am taking it as some 10 hertz or 10 per second. 10 hertz or 10 per second, right? So we know means if you provide a light ray of 10 hertz frequency, then only it can emit the electrons, right? Three different cases I am taking. The first case, here I am supplying a light ray. I am supplying a light ray of VI, incident frequency of 5 seconds inverse. Now tell me, so actually what is the minimum frequency that would require for this metal to cause the photoelectric effect? Minimum 10 hertz or 10 per second. But here, what is the actual radiation or what is the actual energy you are providing to the metal? 5. Then can it cause the photoelectric effect? Then no photoelectric effect. No photoelectric effect. Understood? When incident mu I is less than mu naught, it is a 5, it is a 10. This is case 1. And case 2, I am taking case 2. This time I am taking what I am taking, a light ray of 15 hertz, means mu I is 15 hertz or 15 per second, which is here mu I 15 and it is 10. It is greater than this one. Then it causes photoelectric effect. And what about our excess frequency? That would convert into kinetic energy, and the electron will have non-zero kinetic energy. It will move with some kinetic energy. The kinetic energy or kinetic frequency must be equal to 15 minus 10, that is 5, right? So this is case 2. And case 3, I am taking this time case 3. What is case 3? Right, so case 3, this time exactly I am providing 10 hertz or 10 per second I am providing. Then just it causes photoelectric effect and the electron will come out of the metal atom, but still it stay back at the surface of the metal. It do not move any kinetic energy. In this case, the kinetic energy of the electron will be 0. So now do you all understand all these three three cases when we observed different radiations or different frequencies are being irradiated with the metal? These three observations will be made. Understood all of you? So now the same observation we will write in here. If mu I means incident, is less than mu naught, then photoelectric effect does not take place. If mu is greater than mu naught, means incident frequency is greater than photoelectric effect. This one, photoelectric effect takes place and photoelectrons has a particular kinetic energy, right? And if it is exactly equal, if incident light frequency is equal to the mu naught threshold frequency, then photoelectric effect will causes, but electron do not have any kinetic energy, that would have zero kinetic energy. Understood? So these are the three observations you have to keep in mind. The same three observations we can apply for energy and as well as wavelength also. Energy and wavelength also, right? Next. Kinetic energy of the photoelectrons depends upon the frequency of the radiation striking the metal surface and is independent of intensity of light radiation. Very simple. Here I am taking one metal surface. To this metal surface, here I am allowing to strike a radiation of what is that? Mu naught, right? Mu naught frequency or mu I. So here mu naught. Let me take, for example, this metal requires 10 frequency, 10 hertz light frequency to emit the electrons. But here I am providing some 50 hertz frequency, a light of 50 hertz frequency. The remaining 40 H will converted into kinetic energy. The remaining 40 H will be converted into kinetic energy. That is the meaning of this observation, right? So next observation, let me go for next observation. Photoelectric effect is evidence of the particle nature. Already in the starting of this session, I have told you that today we are going to discuss about a very interesting topic, that is supporting the particle nature of the light. Yes, obviously. Right. The kinetic energy of photoelectron is given by K is equal to half mv square, and we will get half is equal to h into nu, incident light frequency, nu naught threshold frequency. Right. What is this? One by one we will discuss. Right. So frequency related means with respect to frequency, what is Ke? K is equal to half mv square, which is equal to, I can write mu naught mu incident minus mu naught. So that is the last observation as we discussed here, half mv square, which is equal to h nu, because E is equal to h nu, no. So here h is a Planck's constant. Energy is equal to, according to Planck's quantum theory, h nu or not. So here mu is the difference of incident to actual required. Right? This is with respect to frequency. In the similar way, you can also elaborate it with energy. That is part 2. We are going to discuss about photoelectric effect part 2. What is this here? Explanation of photoelectric effect was done by Sir Einstein. Einstein also explained the same concept in his own method. So what is this? With the help of quantum theory of electromagnetic radiation, photoelectric effect was explained. Means Einstein correlated this phenomenon with the help of photoelectric effect, right, and electromagnetic radiation. What Einstein has told: when a metal surface is irradiated with a light of certain frequency called threshold frequency, the energy of the radiation is transferred to the electron of the metal atom. It results in ejection of electrons, right? So the same thing he had, right? Now we know that, for example, this is a metal, and if it is irradiated with a frequency of mu I, so what is the energy of this light ray? According to the Planck's quantum theory, E is equal to h nu or not. In this case, it is h mu I. And if the threshold frequency of this metal is mu naught, what you can write? Threshold energy E is equal to h mu naught. In this way, so this is called as some amount of energy transferred required. This one, some amount of energy transferred is required to overcome the electrostatic attraction forces between nucleus and valency shell. So this energy is called work function. This energy is called as work function. What is work function means? It is very simple. It is like ionization energy. The minimum amount of energy required to remove an electron from its outermost shell is called as work function, right? So work function is denoted with W. The remaining part of the energy means, for example, let me take here one example. I am taking one metal. Actually, it requires some 20 kilojoules energy to cause photoelectric effect, but I am providing some 35 kilojoules energy. What about excess 15 kilojoules? That will convert into the kinetic energy. So from this, what I can say, if I want to calculate kinetic energy, that would be 35 minus 20 or not. 35 is what? Energy associated with incident radiation minus, right? What is 20? That is energy associated with a threshold frequency E naught, threshold work function. So E naught, that is 35 minus 20, that is equal to 50. This is energy related. In the similar way, we can also correlate it with a wavelength, and as well as, right, the total energy of the radiation absorbed by the metal atom, sum of the work function and its kinetic energy. Means E is equal to EI is equal to KE plus, right, work function W. So if I want to know the Ke value, Ke is equal to what I can write? Incident energy minus work function will give us the maximum kinetic energy of the gas molecule. right? So this is a formula. H nu means what? According to Planck's quantum theory, instead of E, I can take H nu. That's why I have given here H nu. You don't confuse. H nu is equal W, where we got of mv square. We know very well that kinetic energy is equal to of mv square. I have substituted Ke value here. Now work function is related to threshold frequency. How? Work function is nothing but energy only. How energy is related to threshold frequency? H nu naught. That is a well-known concept. Next, right. H nu naught, H nu naught plus half mv square. Right. So from this we can derive the formula. All these formulas are based on mathematical only. So see here, half mv square is equal to h nu minus h nu naught. But I know that mu is equal to c by lambda, and mu naught is equal to what I can write c by lambda naught, because c is constant always. So if I substitute, I will get this one, where m is the mass of the electron, v is the velocity of the photoelectron. Greater the intensity of radiations, higher is the photoelectric effect. If intensity increases, kinetic energy never increases. See here, kinetic energy of the ejected electron is directly proportional to frequency, right? And photoelectric current PEC is directly proportional to intensity. Photoelectric current is independent of frequency. It does not depend, right? At the same time, kinetic energy of the ejected electrons also independent of intensity. Do you all understand? Right. So this is the next slide, and here we are going to discuss, right? So photoelectric effect numericals. In the next class, we are going to discuss about photoelectric effect and the numericals related to photoelectrical effect, because there were so many previous questions from this topic. It is a very important. Thank you so much, and thank you for watching this video. Please share, subscribe, and please click on the bell icon. If you click on the bell icon, whenever I upload a new lesson, you will get a notification, so that without later you can see and you can follow. Thank you.